Our next speaker this morning is Dr. Michael Trachtenberg from, he's chief, I guess he's the executive officer and founder of a company called Carbozyme. And Michael has a very long-standing interest in understanding energy. He's going to talk about, the title of his talk is Energy and the Environment.
Thank you very much, Paul. Good morning. Good to be here again. So I'd like to start a little bit by touching on some of the highlights that Jerry just spoke about. Energy is, as we all know, central to every economic growth, but more importantly, it's always been, historically, the basis of cultural complexity, and it always will be. Right now, the energy economy supports the development of materials and processes that then give us product economy and the service economy, and has been, Paul noted, the servitization. Yes, I realize that's a not very good word, but the servitization is the embodiment of service in the product that now serves as a basis for making decisions as to which kind of product to choose. It's not simply having energy, but the energy has to be refined. And that means that it has to be flexible, portable, reliable, consistent, and convenient. One of the properties of electricity that makes it so attractive is that it satisfies all of these goals. And so, as such, it gets a great deal more attention. We can see this in the history. If one thinks about how power was used in early industrial applications, as you know, water power was the driver. And so as a consequence, the energy source and the production of finished materials were physically coupled. When we moved to early electricity situations, then there were three elements. One is the source of the raw energy, if you like, or the power, the energy, the stream that is moving, which was the earliest source of electric generation. There was also very early electric power generation using natural gas, long before oil or coal were the bases. And then that electricity that was generated was transported via this grid, including the wooden sticks that Jerry spoke about. And the key element was line loss. So you had to have two components. You had to have a running stream, not simply to drive your turbines, but more importantly, as you'll see later, to cool your power plant. And you had to have your power plant as close as possible to your end use so that you didn't suffer unacceptable line losses. As we moved up using that same paradigm, you'll see that the location of power plants was always along rivers, streams, lakes, or oceans. And that was because cooling water is so imperative. Second, it had to be close to the site at which it was being used for the reasons noted. And that meant that the third element, which was the transportation of coal or oil, was the fungible basis, gave rise to very long-haul railroads, and coal remains the #1 product that is transported by rail today. What is changing in the next generation is the ability to use less water, and that's coupled with high voltage lines. That means that you can now move the power plant away from the site at which that energy, the final energy, is going to be used. You can move it closer to the mine mouth. You can use distributed wind or solar, as may be the case, and many certainly have suggested the use of large areas in the desert for solar. And Ted Turner is full well aware of this. You may know that he is currently the largest private landowner in the United States, having purchased large swaths of areas in Nevada and Arizona, New Mexico, in order to build solar facilities. And those will depend totally on high voltage lines to distribute the power back to end-use sites. Here is a large concept, one of many, here for Europe, to underscore the idea of these massive grid systems that could use multiple sources of energy, of power generation, to be distributed all over North Africa, the Near East, and Europe. There are other models for this that go through South America and North America. In fact, there is a model that covers the entire world in an integrated grid system, all of which depends on low line loss. So what is the driver? Well, it's already been said and everyone knows. It is really two things: increased population, increased standard of living. And I hope that this comes out. Okay. Even though I can't give you the exact numbers, very odd, of increase, ultimately there's going to be, is predicted to be a 92% increase in electricity demand by 2030 worldwide. This underscores all of the issues that Jerry said. So we're moving towards a greatly more electrified power system. Okay. What are the consequences? Well, here's one estimate that we did. If we look at the effect of electrification of vehicles, going to electric vehicles, what one sees is that we have now moved that CO2 generation from the distributed sources to point sources if we use a standard hydrocarbon production model. And so the total amount of CO2 moves from 41% at power generation sites to 59%. Right. And that means presumably that it will be easier to capture and easier to distribute for carbon capture and storage. Well, there have been a lot of folks for many, many years who have been concerned about whether we can accomplish technologically all of these ends. This is just a short list of the people. And what's problematic about the presentations here is that they are only broad-based descriptors. There is no ability in these expressions to quantify or to predict what's going to happen. Now, Meadows, of course, in Club of Rome issue, both in 72 and 204, and then Turner out of Cicero in Australia, in fact, looked at some of the predictors, and what they found was that rates of growth of technology and its implementation were pretty much what they predicted. So they were really very nervous about whether technology is going to solve the problem. I think the big change occurred in the papers by Lester and Finan out of MIT. And even though you can't, look at that, very cool. What they did was to differentiate the Kaya relationship that you saw on the previous slide, where Y over P is the most important measure of productivity, that is economic output per unit population. And so if you look at it this way, they now have derived a certain number of conclusions. In specific, if you look at the rate of growth of population in the United States over the last 25 years, the rate of growth of GDP, the rate of changes in technology and its implementation, what one sees is that if you're going to achieve the level of decarbonization that we have committed to, that we are limited to a 1% growth in the economy, something that is considerably below what has been the historic case and considered by most unacceptable. Second, if the economy grows at 2%, then the best decarbonization processes would fail to achieve the ends unless we talk about the very aggressive ultraviolet plan that Jerry just described. So they conclude, as all tech types do, as we do, that there's an overwhelming need for continuous technological development and a huge investment so that we should have something akin to a war status in terms of investment if we are going to achieve these ends. So I'd like to discuss a couple of candidate solutions, including some of the recent work that we have done. So obviously, in order to get Y over P down, you can decrease the demand side, aside from GDP, et cetera. It's really a matter of getting rid of inefficiencies. The discussions about smart grids address that issue. The idea of putting meters on in everybody's apartment or house so that you can understand how much electricity is really costing you and decide when and how to use it is part of the smart grid concept. On the supply side, again, it's an efficiency issue. Let me speak to that right now. The average efficiency of coal-burning power plants in the United States is about 33%, with the least efficient plant at 25%. That's in Dorchester, Massachusetts, if you like. And if you were to install ultra-supercritical power plants of the kind that have been developed in Germany, you could have 45 to 48% efficiency. That is a dramatic 50% gain. And in an industry that considers a 1% improvement heroic, 50% is unbelievable. Okay. If you look at some of the more recent natural gas combined cycle plants, you have efficiencies of over 60%. If you look at the IGCC operations, particularly the ones that General Electric is advertising as power islands, they're claiming close to 50% efficiency. So there are ways to continue to use fossil fuels much more dramatically than we are using them today. And I will point out that if we look, as Jerry pointed out with regard to the Clean Air Act and responses that were carried out, what we're going to see is that the first responses in the power industry will not be carbon capture. They will be introduction of efficiencies, because the long-term economic gains are much better to use that approach. We can also start to burn virtually everything we can, all right? So pyrolysis is now becoming a much more accepted notion, and one can think about Staten Island as an ultimate power plant. Maybe not. Okay. There is a concern about control. CCS, of course, is the current model, and we'll discuss that in a moment in some detail. There has been a real rise in concern about geoengineering. 2 books recently came out. One is called Hack the Planet, and the other is The Cool Planet, both of which discuss geoengineering activities. And we have faculty members here at Rutgers, particularly, let's see, Dr. Bunzel in philosophy, and remind me who's, and Alan Robach, who have been looking at Pinatubo type effects and whether they would be beneficial. Their only effect is really to decrease the temperature. They do nothing with regard to ocean acidification, for example. And the complexities of trying to control distributed weather patterns are in no way addressed. So I took a slide out because there wasn't enough time, but it's very curious that global warming deniers are also the folks who are most positive about geoengineering as the last-ditch attempt to prevent any cataclysmic damage. That's a very peculiar bedfellows. And then there's the alternate technologies that have been discussed in terms of solar and wind and so on. Let me point out there is an effect that has been identified. We talked about decrease in GDP. Well, the recent recession has led to a 9% decrease in CO2. It is far and away the biggest lever in controlling CO2. Then there was some discussion about how much money we spend on new energy forms. And the amount of money we spend on 2 elements dealing with ourselves personally, which is healthcare and agriculture, developing the energy, if you will, the food to power biological systems, dwarfs the total amount of energy that we spend, amount of money that we spend on energy and energy improvement. So if we expect to reach these goals without suffering the downsides, we really have to change our orientation and perspective. So there are a number of ways. This is the way I look at energy production options. I divide it into hydrocarbon and non-hydrocarbon sources, and then the renewable and non-renewable hydrocarbons. So Jerry already alluded to the fact that we can use massive energy storage, MES, as a vehicle for stabilizing both all kinds of episodic energy generation in the form of wind, solar, and ocean systems. The round-trip efficiency is what is of concern, and flywheels, at least under controlled conditions, are in the 90% round trip efficiency area right now. This is really very, very dramatic. It means that you can put a lot of that energy, certainly from wind that's occurring at night, into your flywheel system and then capture it at peak demand points. There's been a lot of talk, and in fact I heard one here at Rutgers about 2 months ago with regard to space-based solar. 7 times the incidence is available as hits the surface of the planet. It's available 24/7. Yes, there are many, many, many problems associated with it, but ultimately it's a great source of energy. Anyway, these of course are some of the pictures, and more importantly what the equivalent is in versus gallons of oil equivalent dollar cost. Now, what is it that prevents our introduction of these novel ideas? As Jerry just pointed out, the electric power industry is extremely conservative because service, delivery, and of reliable, consistent power is key. So if you put that at risk, if you provide brownouts and blackouts, you already are familiar with the kind of distress California exhibited and all of the dismissal of third world type solutions. So one can't do this. It's the increased efficiency and improved implementation is really an economic and political decision, as Peter pointed out a little while ago. We have to get folks immobilized. Technology is only an enabling opportunity. When it doesn't exist, then the political and economic forces can claim there is no solution, or the solution is too expensive, or the solution is too unreliable. And so a very high barrier, a high bar is set in order to introduce new ideas. On the other hand, as you all know, when France decided it was going to go nuclear, that was a command and control fiat. When China has made various decisions, those two are command and control, and they have worked surprisingly well. Granted, there are lots of problems that I won't hide in the Chinese situation. Anyway, what happens is there are 3 ways to burn to get the energy out of hydrocarbons, essentially pre-combustion, oxy-combustion, and post-combustion. Almost all of the current power plants in the United States are post-combustion. There are, I think, about 6 pre-combustion or IGCC plants available. And whether you're using old solar-generated energy sources or new current solar energy sources, we're still committing to burning them and using heat to drive a steam generator, et cetera. That's weird. Okay. The DOE has set some goals that we have to pay attention to with respect to cleanup of carbon dioxide from post-combustion systems and oxy-combustion systems. In specific, they want a parasitic load of less than 20%. The main reason for this, believe it or not, is that if we exceed 30%, we do not have the infrastructure capacity to deliver the amount of coal that is needed to support the cost of capturing the CO2. So we suddenly get an infrastructure round. And the second is to minimize additional cost of electricity to under 35%. Current amine solutions, as you'll see, are in the 25 to 50% parasitic load range. So they're not qualifying for this criterion. The way we've approached the problem is to look at 3 issues. How to maximize mass transfer, in other words, how do you capture that CO2 and convert it to something? How do you minimize the amount of energy that is needed, not simply to capture the CO2, which transforms it into another chemical form, but then to release it as CO2, because that CO2 has to be put into a pipeline, so that all of the absorption and adsorption processes are nothing more than enrichment. They're separation and enrichment processes that are taking a dilute stream, 15%, let's say from a coal plant, 4 to 8% coming from a natural gas plant, and are driving it to an excess of 95% fraction. They're taking it at under 1 atmosphere, and they're driving it to about 2,400 psi. All of that is necessary in order to put it into a pipeline. So here are a couple of the strategies that people are looking at, various chemistries. We're currently very much involved with Jing Li here at Rutgers in looking at MOFs, an exciting new area, metal organic frameworks. But given my background, we've looked primarily at carbonic anhydrase. This is an enzyme that is keeping all of you alive right now. It is in your blood. It is in every tissue. There are about 14 variants that are keeping you operating as we speak. And it is the most efficient carbon capture system known. So let me spend a couple of minutes telling you about that. What it does fundamentally is convert water into zinc hydroxide. It's a zinc atom in the center of the enzyme, as shown on the left. And then, there we are. Thank you. So water is taken in here, converted into zinc hydroxide, reacts with the CO2 to give you a bicarbonate, and the bicarbonate is released. That's the forward reaction, and the reverse reaction, of course, is the opposite. This is some of the pretty pictures that we all have to show because they're so beautiful of the various enzymes. This is CA2 is what's in your blood. This gamma CA is present in methanogens, and it has a very interesting property, and that is that it operates at high temperature. This is critical because the outlet temperature from a power plant is about 50 degrees C. This enzyme on the left is cooked at 43. Not very useful. Okay. So you need to find something that operates at much higher temperature. Here are some data that we've recently developed because a key issue in dealing with enzymes is being able to produce very large quantities and being able to purify them at low cost. And what you see on the right here is the massive overexpression of this high temperature carbonic anhydrase, and as you can see in this band, excellent purification. This is a breakthrough that we've just accomplished in league with collaborators who are formerly at Princeton. The second thing you see is the stability of this enzyme even when held at high temperature for a considerable period of time. So this is the catalyzed rate and the uncatalyzed rate of CO2 going into solution. You can see the gain that you get by using a catalyst, and most importantly, the high stability that we've been able to achieve. This is really very important because the cost of enzyme and the stability of enzyme has been one of those bugaboos that has kept people in the power industry from believing that biological catalysts could have any relevance. We designed early on, and I'll show you we've now moved away from this, a very simple scheme. This is a cut of a hollow fiber, a little straw that is microporous. It's about 1/3 of a hair in diameter. It is separated by another 1/3 of a hair in spacing. It's a liquid film contained liquid membrane, and then there is a second such straw. So what happens is that the flue gas coming from the enriched in CO2, 15% CO2 comes in. At the gas-liquid interface, it's converted by carbonic anhydrase into bicarbonate. And at the next gas-liquid interface, it is converted back to CO2 and extracted in part by use of a vacuum to get you a rich CO2. The CO2 coming out here is about just under 50% wet, and when dried is 95%. And this is critical to get it into the pipeline. We accomplish this by some fancy stuff of some microporous membranes. Here's what the surface looks like. And we organize them in very tight spirals so that the geometry is extremely well controlled and has very massive surface to volume. This is about 1,500 meters squared per meter cubed. This is a very, very large number. But to put this in perspective, you are generating about 1 kilogram of CO2 every day. You're expiring at about 4%, which means you look like a natural gas power plant. And in order to accomplish this, you have a lung structure which when fully utilized is about the surface area of a tennis court. So you are actually devoting a great deal of yourself in order just to manage your CO2 levels. This gives you an idea of the flux, which is the most important element here. There we go. That increases with CO2. So we've been able to demonstrate capturing CO2 from everything from air, actually well beyond this, into cement plant emissions quite efficiently. This is just a schematic of our latest absorber-desorber design, but what's important is that for a 400 megawatt power plant, we're using 78 megawatts of power. That's a 15% parasitic load. You remember the bogey we were shooting for was less than 20%. And the cost of electricity here looks like it's under 33%. So at least in our most recent large-scale laboratory events, we have achieved the DOE goals, and we're very excited about this. When implemented, the system would look something like this. Here's your boiler. This is the apparatus for removing NOx, particles, SOx. And you can see the CO2 relatively increasing. We need an additional polisher because enzymes are in fact sensitive to the acidification that the SOx will generate. Here's an example of such a similar kind of system in use in an EOR facility, and ultimately you've got to compress that CO2, clean it up to get rid of any residual gases that the pipeline company will not accept. So your function is really to take this rather dirty stream at low CO2 and low pressure, clean it up so that it is very high concentration CO2 at very high pressure, and then deliver it to the pipe at the plant gate to the pipeline provider, who will now transport it to some geologic storage site in order to put it underground into a saline reservoir or into an existing oil well for purposes of enhanced oil recovery. So that's really what carbon capture and storage means. It means carbon capture, transport, storage, and then once it is below ground, you have an ongoing monitoring, measurement, and verification exercise. Well, this sounds all really very neat. Why isn't it happening? Well, there are economic and political positions that are not very much in support of this, and as I explained a few moments ago, it is a wiser use of capital for power companies to increase their efficiency or to use fuel switching than it is to install this new expensive cleanup equipment, number one. Number two, new regulations have to be established. They exist in very few places. One of the major ones, of course, is Texas, where the Texas Railroad Commission controls the transport of everything, including all of the pipelines that have been used in the Permian Basin for enhanced oil recovery. Then the pipelines must be installed. Interestingly, we not only have outsourced our power and production, it turns out we have even outsourced and sold a lot of our capacity to lay pipeline. Much of the equipment that is necessary for installing pipeline has actually been sold to the Chinese. We have to build new equipment just to reestablish our ability to lay pipeline. Then there are the issues known as NIMBY and NUMBY. For those of you not familiar with the acronym, that means not in my backyard and not under my backyard. And this is not a problem here alone. There have been a large number of studies sampling attitudes in countries around the world, and the fear of putting CO2 underground anywhere near you greatly exceeds the fear of putting natural gas into storage caverns. Okay. And the reason is that the Lake Nyos event some years ago in Africa has gotten so much PR that it has become an urban legend. Those of you who are not familiar with this, there is an extinct volcano There is a lake called Lake Nyos. There is a CO2 bed underneath there that bubbles up periodically, and every now and again it sort of explodes. Well, if you have CO2 is heavier than air, if you happen to live in this valley, you are now covered with CO2. Unfortunately, this is not very good for longevity. On the other hand, those of you who have gone to Yellowstone also have stood on top of a huge lake of CO2. You have seen it bubble up, and you are here to tell about it. The reason is that you are now towards the top of a hill, even in the valley, and that CO2 is running downhill. So it's not trapped in the geologic formation. Okay. Nonetheless, everybody is certain that, like radon, it is going to percolate up through your basement and not be very good for you. So there's a really serious issue here. Even in Germany, to close on that, RWE and Vattenfall just installed a oxy-fuel plant, ran a pipeline to what they thought was going to be a geologic storage site, and are just having a heck of a time getting approvals. So this is not a good thing. Insurance requirements. Let me give you one example. I heard a talk recently by the governor of the state of Montana. Turns out that if you want to get access to what's called the pore space, that is the space between grains of stone or clay underground, that space that's currently occupied by water, which you would now displace by putting CO2 in, and therefore that water's got to go somewhere, whether it's lateral or vertical. There are quite a number of lakes that are going to be formed. You have purchased, let's say you purchased the rights to an acre. You have the ability to fill up that pore space in that acre. However, should your CO2 leak out beyond the boundaries into the adjacent acre, that is considered trespass. And you are now liable for suit, particularly if the consequence might be, for example, diverting water fields, altering the ability of an adjacent leased area to produce oil or gas, or a wide variety of other complaints that one might come upon. And so there's going to be litigation. So I will tell you that one of the major problems associated with storage is that it is going to be a long-term employment contract for regulators and lawyers, and a huge expense to everyone else. So here are a couple of examples across the nation. This is a picture of CO2 generation sites. And I want you to see if you can remember this, because we're going to map it on CO2 storage sites in the next illustration. And you can see that there are oil fields and unminable coal seams and saline reservoirs. And just to help you, we'll go back for a moment. You can see that a lot of them are underlying areas here and here. And the Gulf has been, with all due respect, the Gulf has been put forth as a major CO2 storage site. All of the depleted oil wells, and maybe not so depleted oil wells, and the salt caverns and so on, are places people would like to see as a storage site. So there is actually a business model for pipelines running to the Gulf to fill this up with CO2. Okay. We would suggest that there is an earlier application, and that is deal with things that have beneficial use. And there are a couple of them that are relevant. One is biofuels. To the extent that algae are excellent biofuel generators, they need the CO2 in order to make those hydrocarbons. And they need huge quantities. So capturing CO2 from power plants and delivering it, preferably close by, so that you don't get into pipeline issues, is a great way to use CO2 and to get a couple bites at the apple. Using CO2 for enhanced oil recovery or enhanced gas recovery, pumping it underground so as to drive that oil. And by the way, that's not simply a pressure issue. CO2, supercritical CO2, operates like a dry cleaning fluid and serves to displace the oil from the soil particles. so that it's moving ahead and one can capture a greater fraction. And even for whitening, creating carbonates in order to keep paper white. So with that, let me close and point out that we stop doing things not because we run out of materials, but because we find more efficient ways to solve the problems that we need to address. And you can see that Germany has already done some of this. So, thank you very much.
One point, I'm increasingly seeing the discussions, way back earlier, when you talk about population control.
Yes.
I think that's a minefield if you want to look into. The research says that if you educate women, you give them the opportunity, population goes down. It's got a lot more collateral benefit for it. It's borne out by research. You only have to look at the anathema that China has become under the circumstances where enforcement along the way. And I think the language around that, population is clearly a driver. It also drives GDP per capita, which is far more important. So
Oh, I totally agree with you. And in fact, some of the more recent projections not coming out of the UN have suggested that population is probably going to cap about 8 billion rather than 10 billion for exactly that reason. Although there are some examples in various countries where the education of women has been seen by men who are currently in control as very threatening. And that has been undermined, unfortunately. But otherwise, the argument's quite right. And that's why I showed that GDP was a much greater lever. And one can't really discuss population for all kinds of historic reasons.
So I have a couple of questions.
Yes?
So there are two issues with the carbon capture and the storage issue. So the storage issue is, to some extent, a geological formation issue of where things are and how stored. And others, a lot of people have worked on this. The capture issue, it seems as if, you have one technology, there's several others out there. Could you explain to us what the cost-benefit analysis are of these various capturing technologies? Air capture,
Right.
for example, would be a great way to do things. We would do it, right?
Yeah, well, we can do it, and I can tell you that it's well over $100 a ton even in our system, whereas we're under $20 a ton looking at it by the technologies we talked about. So parasitic load and cost of energy ultimately get you into both the capital expense and the operating expense that is needed to maintain any kind of CO2 capture system. So what this comes to is dollars per ton of CO2. The tech guys usually express it in terms of energy as megajoules per ton of CO2, and that's not quite the same as dollars per ton for various reasons. But of the various methods that I'm familiar with, so the most common one are amines that have been around since 1931. The bicarbonate methods have been around since about I think it was 1916 or thereabouts. So both of those technologies are old chemistry, so to speak. Nonetheless, amines have undergone considerable development over the last 10 years or so as to decrease the energy, the parasitic load from something on the order of 50% down to the very most efficient amines available today, which are about 23 to 25%. Okay? The adsorptive methods have not yet shown that same kind of efficiency. There are also some efforts to try to make pores in membranes that are exactly the molecular size, the atomic size of CO2. So CO2 being a linear molecule would be forced to move through in an axial fashion. And the idea being that other molecules that are somewhat larger would not fit into these holes. There are also some new electrochemical driving systems out of Argonne National Labs that we've participated in. We've just filed patents on that, as well as some that have come out of Lawrence Livermore National Labs. But all in all, just about any technique that anyone can imagine is being tried. And the competition is going to be about cost and reliability, stability, and how much the power companies believe this is going to be effective over the long term that's worth their investment. We're talking about investments for cleanup systems on the order of $300 million. So these decisions will not be taken lightly. Yes?
Could you say something about the relative opportunities and merits and drawbacks of capture and sequestration relative to reducing the carbon dioxide chemically to make formates, methanol, and so on?
That's a very good question. And again, that's an energy cost question, and what the ultimate value of the end product is that you might generate. For example, there have been some efforts looking at both carbon monoxide and ethanol, methanol, as you know. Right now, the energy costs for reducing CO2 are higher than they are expected to be for burying it. So that's again a technical efficiency issue that will be determined. And I expect a lot of very novel ideas will come up. My suspicion is that by the time we get around to storing large quantities of CO2, new technologies will indeed arise that will treat it chemically or electrochemically in order to reduce it and recycle it.